All right, time for our third and final video of the day. We're going to talk about some properties of sets, and particularly open and closed sets, and how these things are detailed. I'm going to do a couple proofs for you today, but I'm also going to kind of hand wave my way through a few proofs because I know you're probably getting tired of watching these just as I'm getting tired of creating them. So first let's talk about unions and intersections of sets. So first thing that you should know is what happens if A and B are open. So if A and B are open sets, then what happens if we take the union of two open sets? Well, then that one is going to be open as well. And we actually talked about this just a little bit in class the other day, but the reason is if I have one set here for A and say another set here for B, then when I combine them, I get the larger set. And well, so therefore if I took some point in A union B, it would have a ball around it, but notice that exact same ball works for the larger set. So I can use the exact same radius about that point and to solve my problem. And for this reason, not only is A union B open, I can take a union of an infinite number of things and still have it be open. So so we'll say for example we'll say alpha in some index set of A sub alpha is open if each A sub alpha is open. Okay, so you might be asking yourself right now, why didn't I just go the union as k goes from 1 to n? Well, when I do that, I assume that my set here is countable, and it turns out it might not be countable. We could have the index be the real number, so each real number could be defining an open set, and then we could take the union of all of those open sets and still get an open set. Because it doesn't matter how many we union together, we'll always still have an open set. Okay, it turns out that intersections aren't quite as friendly. So let's talk just a little bit about intersections. So what do we notice? If A and B are open sets, then A intersect B is still an open set. So let's kind of do the same picture I had earlier, where I have A and B, and then A intersect B is just that little piece in the middle. So it's just that piece right there in the middle. And what I can do is if I have some x here inside the intersection, then, well, there were two open balls, so there might be an open ball. Let's use different colors. So there might be an open ball that fits it within B, right? So that's the ball of radius 1 about x. But then we might have a different open ball that fits it within A. So maybe that one right there is going to be the open ball of radius 2 about x. Maybe I should have done A first, but I guess it doesn't matter. But what do? I just choose the smaller one. So the smaller one fits, right? So I use, I just let R be the minimum of R1 and R2. And so that works perfectly fine. And so the intersection of open sets is always an open set. However, I want to notice this minimum only exists when we have a finite number of terms. So this actually fails whenever we have an infinite number of terms. So we can't intersect an infinite number of open sets. And be guaranteed. I mean, it could be open, but we can't take an infinite intersection of open sets and be guaranteed an open set. So let's just do a quick example for that, and you'll see why that has to be the case. The example that I like the best is what if we let each of our sets, so I will let my set A sub n be the open set from negative 1 over n to 1 over n, and then what you'll notice is my very first open set is right here, and we'll just use the real numbers. And so there's my first open set from negative 1 to 1. My second open set is negative 1/2 to 1/2. My third open set is negative 1/3 to to 1/3, and then we just kind of keep going in this way. But what happens if I take the intersection from 1 to infinity of all these ANs? Well, I'm left with, there's only one point that's left that's in the intersection of every one of those sets, and it's just the point 0 alone. And what we saw is that a single point must be closed. So we can't take an infinite intersection, but any finite intersection will be just fine. Okay, what if we flip the script a little bit and ask about closed sets? Well, to ask about closed sets, all we have to do is remember one important theorem that you got from your transitions class, and it was De Morgan's theorem. And De Morgan's theorem simply says that if you have the union of two closed sets, we take the complement of it, then that is A complement intersect B complement. And similarly, if we have the intersection complement, then that's A complement union B complement. And what you'll notice is, talk about closed sets, we'll talk about the complement of them. And so because of De Morgan's laws, we see that the exact opposite rules apply as to open sets. So for open sets, when we took the union of them, it was still open, but when we took an infinite union, it was still open. But for closed sets, it's going to be the opposite. So it's going to be that A intersect B is closed. Or let's do union. We do A union B is closed, but an infinite union might not be. Now, why is that? That's because when we're doing the proof that A union B is closed, we're going to be using this theorem, so we're actually going to be using the facts about A complement intersect B complement, and we know that infinite intersections might not be open, so infinite unions of closed sets might not be closed. And then similarly, I'll go A intersect B is closed, and an infinite intersection is as well. Okay, so we can put together open and closed sets really quickly and really efficiently. We have two more terms. We have a term called the interior and the closure. The interior, I'll denote E with a little circle, E naught. And what is this? This is the union of every set V such that V is open and V is a subset of our set E. Okay, and then similarly, I'll have the closure. So let's define the closure in this way. E closure, I'll put the little bar above it, and this is kind of why I said we might use the bar for closed balls earlier. What we'll see is the closure of an open ball is a closed ball, and the closure is the intersection of every set B such that B is closed and B contains E. So B is larger than E. So let's just think about this real quick. Let me draw, let's draw my set here, which maybe I'll have parts of it be open and parts of it be closed. And then what we'll do is to come up with the interior, then we'll just take every open set. So we'll take an open set here, and an open set here, and an open set here. So we'll take larger and larger open sets, and then what you'll notice is eventually we'll get an open set that looks something like this. Maybe I should have drawn all those dots. Now I have to tap my... And so eventually we'll get an open set that looks like this, that basically is just hugging the outside edge. And if we take the union of all of them, that's what we get. So the union of this thing looks like that. So it's like we took all of our open sets and let them get larger and larger. And so in some ways, we could think of this A interior as like the largest open set that fits inside of E. And it's similarly, as we talk the closure, well, we could have some big closed set around here, some closed set within that. And since we're taking intersections, the intersections get smaller, and eventually we get that intersection that just closes it. So E closure is like the smallest closed set. So one thing you could think of this is the largest open set in E, and this is the smallest closed set around E. So if we think of this again, just to say it one more time, what you might think is, well, let's take a ball here and let's have the ball be like, let's make the left half be open and the right half be closed, and then ask, what do we get? Well, the interior is the largest open set, and so what we do is we just take that side off, and the closure is the smallest closed set, and so it's just that set that includes the outside edge. So this is kind of the way we think about closure and interior. Okay, so a few things that are pretty obvious about closure and interior. First, the interior has to be a subset of E, and then that E has to be a subset of E closure. So closure has to be bigger than E. The interior has to be inside of E, and so they have to have this relationship. So also, if E is an open set, then the interior is equal to E. It is the largest open set that fits inside. If E is closed, then E closure is equal to E. So if it's closed or open, then if it's open, then the interior is the same, and if it's closure, then if it's closed, then the closure is the same. Finally, if V is any open set, if V is open and V is inside of E, then V must be inside of the interior of E. And that makes sense because E is like the largest open set, so V would have to be inside of it. And then there's the analogous for closed. And B contains E, then B contains B closure. So this is kind of the exact same thing there. We have one more term, and it's a term called the boundary, and we often write the boundary with kind of this partial derivative type symbol, the boundary of E. And what is the boundary of E? Well, we'll define it as this. We'll define it as the set of all x such that for all r greater than 0, the ball of radius r about x intersect E is not empty, and the ball of radius r about x intersect E complement is not empty. So that is how we'll define the boundary. And let's just think about what that means for a second. So if I just draw a picture like, say I have a ball here, and if I just asked you, where's the boundary? Well, you'd probably say, oh, it's right over here on the edge. And notice what that means. That means if I draw a ball around it, I have two things. On one hand, I have a handful of points that are intersected with E. So I have a handful of points that are on the inside here. But then I also, at the same time, have a handful of points that are on the outside here. So what you can see is that my intersection has both points that intersect with E, so both points inside of E and points that are outside of E. So it has both points in it. So that's what it means to be in the boundary. Take any little neighborhood around it, any little ball around it, and that ball has both points inside and outside of E. And that kind of intuitively makes sense as to what boundary should mean. So let's just do, there's going to be some examples. I think I'm only going to do one example that I like. This example is going to look like this. It's going to be in R2. And I'm going to call it, make my set I'm going to get the set, the ball of radius 1 about the point -2, 0. And then I will union that with the ball of radius 1 about the point +2, 0. And then I will union that with this line segment from -1 to 1 cross the 0. So what does this -1 to 1 cross 0 mean? It means I take x from -1 to 1 and then add a y value of 0 to it. So what does this look like? If I were to graph this ball would look like here, if I put this at x equals -2, and then I have another point here at x equals +2, then I would have a ball around each of radius 1. and then I have a line segment that goes between those two balls like that. You could almost, I think the book did a similar example, and I think they called it like barbells or dumbbells or something as you look at it. Okay, and then let's just quickly think, well, what is each of our different pieces? What is the interior? Well, the interior is actually only these parts that are inside of here. So the middle of the dumbbell gets completely deleted, and so the interior is just that shaded edge and that shaded edge. So it's that ball, it's that first ball union that second ball. And then I'm going to hack my notation, leave off my zeros because I'm feeling a little bit lazy. So what's our closure going to be? Well, the closure is what we get when we include all of the points that are around here. So the closure is going to have both dumbbells and the little section between it. So the closure is going to look like this. And so it would be like the closed ball and the closed ball and that line. Finally, what's the boundary? Well, the boundary is just the part that's on the edge. So the boundary is just this line and this circle right around here. So maybe I did a little bit of a disservice with the way I drew my picture. So my closure and my interior should both also include all points in the middle, and the boundary doesn't include the points in the middle. It's just that outside edge. And so I could say it's the set where the radius equals 1 for over here and where it equals 1 over here. So there's an example. We could do lots of examples in a lot of different settings, but this is just to get a picture of what we mean by these words: interior, closure, and boundary. Let's do one proof, and I think this proof is a good one because it kind of is of the degree of difficulty that would be kind of homework test level proof, and it gets in an important part, and that is that the boundary of E equals the closure minus the interior. So if you look, you'll notice the interior is the inside parts, and so if we took this closure and we took out the inside parts, then we would have the boundary. So the boundary was just all the pieces that are in the closure and not in the interior. So we're going to do this as a couple different pieces. So part number 1, we're going to prove that if X is in the boundary of E, then X is, if X is in the boundary of E, then X is in E closure, and so that's going to show us that, that's going to do that one piece. I'm not going to do like every little piece. I mean, I guess technically we should show that the boundary of E is a subset of this, and that that's a subset of that, and I think I'm just going to show the boundary of E has to be a subset of E complement and not a subset of and you know, has nothing in common with E interior. And I think this will convince us that it's proof. So here's a couple proofs that I think we could do. If X is in the boundary, then X is not in the closure. So what am I going to do? Well, remember my closure definition means, and sorry, I'm running way over here, means for all B, if B is closed and B is, it's the union of all B where B is closed and B is a subset of E. So I have to start with an arbitrary closed set in order to make this proof go. So I'm going to let B be a closed set, and E be a subset of B. So in other words, B is one of those sets that was in the intersection of the closure, right? Because E closure is the intersection of all of those B's. Sorry, it's the intersection of all those B's. Okay, so let B be a closed set and E not be a and E a subset of B. And then I'm going to, by contradiction, I'm going to say, well, what if X was not in B? So in other words, what if our boundary element was not in E closure? Okay, so by contradiction, if X was not in this closed set, if X was not in this closed set, then there would have to exist some epsilon greater than 0 such that B sub epsilon of X is a subset of B complement because B complement, since B complement is open. So I took some closed set around E. So let's draw my picture here. So here's E, and here's some closed set B. And then if I took an X outside of B, then the outside is open, so I can make an open interval that contains within that. But then what does that mean? But that means that B sub epsilon X intersect E would have to be the empty set because E is completely contained because this BE is completely contained in B closure and E is contained in B, so it's definitely E is not definitely has no intersection with B closure. So B sub epsilon X intersect E is the empty set, but that just means that X must be, but that creates a contradiction. Let me erase this and make this look a little bit nicer. But that creates a contradiction. So therefore, X must be an element of B, but since B was arbitrary, that means X must be an element of E closure because every single B this statement's true for. So X is an element of every B. So X must be an element of B closure. So we saw the first thing, that if X is in the boundary, then X is in E closure. Now let's do the opposite, and let's come here and say, well, what happens if X is if X is in the boundary, can X be in the interior? We're going to say if X is in the boundary, then X is not in the interior. This will show us that everything in the boundary is in the closure and is not in the interior. So that gets us exactly where we want to go. Okay, so great. So let's come here and let's remember, what does E interior mean? E interior is the union of all the open sets V. So I'm going to take an arbitrary open set V, and so I'll let V be open, and I will let V be a subset of E. So here's my picture again. Here's E, and now we took some smaller subset here, which is subset V. And then I'm going to do the exact same game that I did just a second ago. I'm going to pick some point in V, and then I'll draw some ball here and show that that point would have to be in the interior. So I'm going to say, by contradiction, if X is in V, then there exists some epsilon greater than 0, such that the ball of radius epsilon about X is completely contained with V. But then what does that mean? That's because V is open. But that means that the ball radius epsilon of X is completely contained with E, which implies that the ball of radius epsilon of X intersect E complement has to be the empty set. Well, and since it's the empty set, that contradicts the fact that X was on the boundary. So X can't be on the boundary, so there's our contradiction. So that means X must not be in this empty set, or be in this open set. But since this was an arbitrary open set, it's not in any of the open sets in E. But that means X must not be in the interior of E. And so I've established this part, I've established that the boundary of E is a subset of E closure minus E interior. And if I wanted, I could be more diligent and go tackle some other parts of the proof. But I think this gets at the heart of how we do proofs with interior closures and boundaries. So what's at the heart of how we do the proofs? We talk about arbitrary open and closed sets. We talk about balls and whether those balls intersect sets or not, and points in the balls. So hopefully it gets you a little bit of picture of how we approach proofs like this, because you'll be asked to do a few like that as we move forward. Okay. Finally, we have a couple theorems that I'm just going to shout at you as you walk out the door. The first is that how do interiors go if we take the union of them? Well, if we take the union of interiors, then we get the subset of A union B interior. However, if we take the intersection of interiors, then we get that this is equal to A intersect B interior. And if you think of why this is, well, when you union A and B, you could potentially get, you're getting a larger set, so you could potentially get some extra elements that add to your interior, that make your interior a little bit larger than just the two that you had to begin with. Compare that, however, to the intersection. It made your set smaller, so the interiors had to constrict. So we couldn't have picked up any extra points in the intersection. Okay. Similarly, the closure is going to work the exact opposite of this. A closure union B closure. Oh, that was supposed to be an A. I said A, I think. A closure union B closure equals A union B closure, but A closure intersect B closure is contains A intersect B closure. And so this is for the same reason that since we're doing intersections, A intersect B could have got smaller, and so its closure could have lost some things. We could have made it a little bit smaller and lost some points when we intersected them. Okay, so So there we go. And finally, boundaries have a couple. The first one, the boundary ones are a little more complicated. Boundary of A union boundary of B contains the boundary of A union B, and then you can kind of see that this should be the case by grouping these intersections and closures together. The one that's a little bit confusing looking is the boundary of A intersect B, which is the boundary of A intersect the boundary of B, union the boundary of B intersect the boundary of A, union the boundary of A intersect the boundary of B. Oh, and I should have put subset like this, right? I should have put subset like this. So this intersection has all of these different pieces to it, which could, you know, this is a little bit confusing. But let me just draw a quick picture for you that maybe helps. So we'll just let this square here be the square A, and then we'll let this square here have this intersection that could be the set B, and then if we intersect A and B, then that's this little piece in the middle. So A intersect B is that very small circle in there, so that means the boundary is just that square. But if we think about these pieces, well, if we wanted to take these two boundaries and intersect them, the boundary of A intersect the boundary of B, well, in fact, all we would get is just these 2 points on the corner, just that point and that point on the corner, because those are the only 2 points that intersect the boundary. So we also have to take A intersect the boundary of B, and that is think of the parts of the boundary of B that go into A, and that gives us kind of that L shape, and then the other one gives us the other L shape. So you can see why we need all 3 pieces to put together our story here. And then I'll let you think a little bit about why it's not an equal sign, and we can kind of come back to that at some point. Okay, so this is a quick explanation of how we think about interior, closure, and boundary theorems, and hopefully this makes a little bit of sense.